Okay, we are going to do exponential modeling day 2 notes now. We just finished exponential modeling day 1 notes, which was about increasing exponential functions, so exponential growth. And this handout is going to be dealing with exponential decay. It goes on page 130 in your math notebook. So please make sure that you have the one that says decreasing exponential models. And it'll be on page 130. And today's date is 5/13. Okay, so what we're going to do here is we're going to talk about a substance or problems where the amount is decreasing by a constant factor over regular time intervals. So one of the applications of this is with in chemistry with either radioactive decay or what we call the half-life of a substance. So we still have to think about identifying the initial amount when we do these problems and the rate at which we are going to be, in this case, decreasing how much we have of this particular substance. So our first question asks us to determine how much material remains after 1 year. So I need to take my 200 kilograms, figure out what 2% of that would be, and then subtract that percentage amount from 200. So 200 times 0.02, we always have to convert those percents to decimals, and that's a 4. So I know that I'm going to have 200 kilograms minus 4, so that's 196. So we'll have 196 kilograms left after 1 year because we're losing 4 kilograms that first year. So just like we did on the last one, we want to think about, is there a number that we could multiply by that would give me the same result of 196 that I got using 2 steps? So there sure is. So what we would want to do, maybe if we write it out like this, 200 minus 200 times that 2% converted to a decimal. And then watch me factor out the 200. So if I factor out 200, we'll get 1 minus that 2%. And that's actually going to be 98 hundredths. And this value is 196. So the single number that I could multiply by is, I could multiply by 98 hundredths, which means that we have 98% left after 1 year. Now we're ready to write our decreasing exponential function. So a of t is equal to 200, the initial amount, times 98 hundredths raised to the t. So each year we're going to have 98% of what we had the year before. And we know that this is going to be decreasing because the base here is between 0 and 1. So our scale factor is smaller than 1. It's going to decrease our growth rate. All right, so here we can figure out the half-life of this substance. The half-life is the amount of time it takes for half of the amount to remain. So half of the amount is going to be when there's 100 kilograms. And that meaning of half-life isn't going to change. Your initial amount and your decay rate might change, but the meaning of half-life won't. It's always going to be the time when there is half of the original amount left. So if we take our 200, let's actually go to our y equals and enter this in, 200 times 0.98 to the x, and then we can go to our table. Now we started with 200. So I should see in my table a starting amount of 200, and then there's that 196 that we got after 1 year. And we want to keep scrolling down in our table until we have 100 kilograms remaining. It's going to take a while. Each year, remember, is 98% of the previous year. Okay, so we're getting close. So there we go. In year 34, we have slightly more than 100 kilograms. In year 35, we have slightly less than 100 kilograms. So the half-life is going to be between the 34th and the 35th year. Okay. So I'll write that on my notes. And that's because A of 34 from my calculator was 100.63. And A of 35 from the calculator was 98.615. Those are rounded, by the way, to 3 decimal places. Whoops, that was 5. All right, so we're seeing an equation when we talk about a decreasing exponential model that's really similar to the one we had before, except instead of adding that percent of increase, we have to subtract that percent of increase. Q sub 0 is still our initial amount. And when we subtract our percent of increase from 1, we're going to get a growth factor that is smaller than 1, which is going to indicate exponential decay. So sometimes we call this decay rather than growth. So you might see that in the textbook or in the homework assignments. Q sub 0 is still our initial amount. And P is our percentage that we're decreasing by each year. All right, let's see if we can write a model and solve this problem. So we are starting with 12,500 residents, and it's decreasing by 4% per year. And we want to find the population in 10 years. So I'm going to give you a minute to start off by writing the P of T equation. All right, so let's pause the recording and maybe work with a partner to write the P of T equation we would use for this decreasing exponential model. Okay, hopefully you've had enough time to work on this problem, and we're going to plug in 12,500. And then we're going to do 1 minus 400ths. Check to make sure that you changed 400ths correctly to a decimal, or 4% correctly to a decimal. And maybe you went ahead and wrote your function out as 9600ths for the growth factor, which is actually a decay factor. All right, now we're not done with this problem. It doesn't just ask us to find the formula. We want to figure out what will be the population, what will be the output when the input is 10 years. So that's P of 10. We'll need the calculator to do this. So I can just take 12,500, multiply it by 0.96 raised to the 10th power, and that's 8,300. There we go, you can see the full number now. 8,310, and this is people, so let's round it to the nearest whole number. So 8,310, and that's choice number 4. Let's keep going. All right, so on this problem, we have an amount of water that the soil can absorb in inches per hour, and we see that it decreases by 30% per hour. So that's my decay rate. And a particular dry soil is initially able to absorb 4 inches of water. So that word initially kind of is the one that clues me in that that's going to be my starting amount. All right, so my A of T formula is going to be my initial amount, which is 4 inches, and then it's decaying, so 1 minus 3 tenths or 30 hundredths to the T. So if we want to do the arithmetic there, we probably would want to write this as 4 times 7 tenths or 4 times 70 hundredths. So this is indicating to me that after each time interval, we have 70% left of what we started with. Notice that that number is smaller than 1, but still positive, which means we're going to be decreasing. All right, so we want to sketch the graph of the function going from 0 to 10. So when time is 0, anything to the 0 power is 1, so we know we're going to have 4. I'm actually going to go ahead and I'm going to put my 4 up here because we're decreasing from 4. All right, and then we wanted to go all the way to 10. So let's grab the calculator again and figure out how much will remain after 10 time intervals. Oops, 70. And you could just write 0.7 but I want you to remember it's a percentage. Okay, so it looks like we've got a decimal amount left, okay, for our rate. And so this is going to be about 0.113, okay, so a really small number, 113. And we'll be decaying down. So we've got to make our graph look curved, like an exponential function that's decreasing. Okay, all right, so in part C it says a steady rainfall of 0.5 inches per hour is flooding the soil. Water will run off the soil when the rainfall rate exceeds the rate at which the soil can absorb the rain. At what time to the nearest tenth of an hour will the runoff start? So here as time passes, my rate is decreasing, but I have rainfall that's constant. So if I go over here to where a half is, I'm just estimating it. I know it's less than 4. That's like my steady rate of rainfall. So in the last problem, we solved a problem graphically by finding the intersection point. And we're going to do the same thing here, because this time t is going to tell me when my rainfall rate is going to be greater than. Okay, sorry about that. We are going to finish solving this problem now. And we need to type in the equation here and 5/10 into y2 and find the intersection point. So 4 times 7/10 to the x and 5/10 here. And we'll set the graphing window up. We know we want to go to 10. And we can set our y max to be 4. Here we go. Okay, so I'm going to model finding the intersection point for you one more time. So second calc intersect, press enter 3 times. And then we can see that that intersection point is at the 0.8 and 5/10. And so what that means is that the runoff is going to start after 5.8 hours. Okay, let's go down and look at this next problem. In this next problem, we have 2 different companies, one whose stock price is increasing at a rate of 4% per week with an initial value of 20, and another whose stock price is crashing at 11% per week, and they have an initial price of $120. So we want to figure out when will the 2 stock prices be the same. Okay, so let's take a look at the functions that we would need to model this. Okay, and you can see here that I have my initial amount and my growth rate. And for the decreasing stock, that initial amount and the growth rate, 1 minus the 11%. So we're going to put these on the calculator and find the intersection point graphically. And that's going to give us the solution to this equation. So we've already done quite a bit of work with the graphing calculator. And what we'll do, I'll just show you in a second here, if we have time, is this one's going to go in y1, and this is going to go in y2, and we will find our intersection point on the graphing calculator from there. So let's see if we can squeeze that in before our time is up. So we need to change our equations, so let's clear these out. And we had 20 times 1.04, 4% growth, to the x. And then we had 120, and it was 0.89 because it was 11% decay rate to the x. Whoops, to the x. And you know, I just think maybe let's try going to 20. Okay, I'm not sure. And I can't settle on my y max being 4 because I know my initial amount of the second stock was 120. So we'll do 150. Count my tens. All right, you can see that the graphing calculator is basically going to give us the same type of graph as you see that I sketched on the side there. I'd already pre-calculated that intersection point using the graphing calculator. And so we're just about out of time, and we can see here that after 11.5 weeks, the stock price will be the same.